In the last lecture, we talked about how to find the electric field from a charged body. It is similar to electric field from point charges, but instead of Q, the charge of the source point charge, we are going to use dq and we are going to perform an integral. So we basically break the charged body into infinitely small pieces. Then we find the electric field from each element, then we add them up. We can categorize the charged bodies into three types: a line, an area, and a volume. That's what we are going to talk about in the next three lectures. In this lecture, let's start with the line. Charge distribution for a line. So suppose we have a line with length L, and the line has a total charge of Q. Then we can define the line charge density as the total charge divided by the length. We can have a constant line charge density throughout the line, or we can have a charge density that is as a function of x. We break the line into small pieces, and for each piece, it has charge of dq. It also equals to the density, the line charge density, times dl for a small segment of the line. Then the electric field at point P from the body, it is simply the integral of the electric field from each pieces, which equals to 1 over 4 pi epsilon naught, integral, and we replace the dq by the line charge density times dl, then over the distance square, and direction is r hat. And I've already mentioned this. The charge doesn't have to be uniformly distributed. We can have a line charge density that is as a function of x. In this lecture, we are going to look at two examples of finding the electric field from charged line. Here's the first example. Consider a finite line segment having a linear charge density that is as a function of x. It is 10 times absolute of x, where x is in meters and the line charge density is in coulombs per meter. So from this function, the linear charge density, we know that as we move further away from the origin, from x equals to 0, the density will be larger. Similarly on the other side, because we have absolute of x. So as we move further away from the origin to the left, the charge density will also be greater. The line segment extends to a length of L on either side of the origin. Point P is at a distance y above the origin. Part A, we want to find the total charge of the rod. And part B, what is the net electric field at point P? You can pause the video right here and try the example by yourself. Then you can continue to watch the video to check your answer. Here's the sketch of the problem. So we have a rod that extends from negative L to L, and the line charge density is 10 times absolute of x. In part A, we want to find the total charge of the rod. Let's first break the rod into infinitely small elements. For example, I'm going to look at this part, this element. Then what is the charge of this small element? dq. The definition of the line charge density is the charge divided by the total length. So for a small dq, it would be the line charge density times the length, which is dl. So dl would be this length. Then the total charge. Q. We need to add up all the dq's from all these small elements. So it would be integral of dq over the line. And dq equals to the line charge density times dl or dx. And the x goes from negative L to L. So they are the lower and upper bounds of the integral. Then I substitute the line charge density. It is 10 times absolute of x, then dx, from negative L to L. Then we can note that since we have the absolute sign, so we have a symmetry about the origin. Lambda of negative x equals lambda of x. Then we can use this symmetry to rewrite the integral for the total charge. Q, it will be twice of the charge from the origin to L. So 2 times the integral from 0 to L of 10x dx. And here we get to a simple integral. This equals 20 times x squared divided by 2. And the bounds are from 0 to L. And we get 10L squared. So that is the total charge of the rod. And in part B, we want to find the net electric field at point P. Here I'm going to use a trick. I'm going to use symmetry. Symmetry is a common trick that we are going to use in this course. On my sketch, I have a red small element on the right. I'm going to draw another element on the left that is symmetry to this element about the origin, which is around here. And let's call the charge of this small element dql, L for left, and the charge of the element on the right, dqr, R for right. Let's find the dql and dqr. Using the line charge density, dql, it equals to the density as a function of x times dx, which is 10 times absolute of x dx. But since the x here is negative, so when I remove the absolute sign, I need to add a negative sign. So it is 10 times negative x dx. How about the dq on the right? It equals to lambda as a function of x dx, which is 10 times absolute of x dx, which equals to 10 times x times dx, since on the right the x is positive. And since I'm using the symmetry, so the x here, they have the same distance to the origin. So these two, they are equal. dql equals to dqr. They are both positive. So when I draw the electric field due to these two small pieces, from dql, I'll get the electric field at point P, something like this. And let's call this del. And from dqr, I'll get electric field pointing in this direction. And let's call this der. And note that since I'm using the symmetry, so this angle equals to this angle. So when I add up these two electric fields, the horizontal components are going to cancel. Furthermore, since their dq is the same, so their y components are equal. So the total electric field from the line, if we write it in components, we get Ex in the I hat direction plus Ey, y component in the j hat direction. We can pair out the small elements like dql and dqr, so all the x components are going to cancel. So the total electric field has Ex, the x component, equals to 0. Now we are going to use this information to find the net electric field from the rod. So we found that by symmetry, the x component of the electric field are going to cancel. So we only need to find the component Ey, which is the integral of the electric field from each small element in the y direction. This equals integral of the Coulomb's constant times dq divided by r squared. And since we are focusing on the y component, so we have to times sine theta. And dq, the charge from each element, it also equals to the density times dx. So let's replace that. It equals to integral of Coulomb's constant times lambda as a function of x times dx divided by r squared times sine theta. We substitute the line charge density. Integral of Coulomb constant times 10 times absolute of x times dx divided by r squared, then times sine theta. And the integral goes from negative L to L. We also found that if we use the symmetry, the corresponding electric field from the other side, their y components are the same. So we can rewrite this integral Ey as twice of the electric field from 0 to L. So 2 times the integral Coulomb constant times 10 times x dx divided by r squared sine theta. And the bounds are from 0 to L. Now I want to write the sine theta in terms of x and y. So we know that the point P has a distance of y away from the origin. So suppose here is my dq, and this is my theta. The vertical line is the distance y, and this is x away from the origin. And the hypotenuse, using the Pythagoras theorem, it equals to square root of x squared plus y squared. So from this triangle, sine theta equals the opposite over the hypotenuse, which is y over square root of x squared plus y squared. Let's substitute this into our integral. So this equals, we can pull out the constant. I pull out the Coulomb constant and the 10, so I get 20 times Coulomb constant times integral of x over r squared. The r here is the distance from the charge to the point. So this hypotenuse is the r. So r squared is x squared plus y squared. Then times sine theta, y over square root of x squared plus y squared. Then dx. So just a quick note. So the x squared plus y squared here is the r squared. And this part is sine theta. The y is a constant. It is the distance from the origin to the point. So I can also pull the y outside of the integral. Let me rewrite the integral as 20 times Coulomb's constant times y times the integral x over x squared plus y squared to the power of 3 over 2, then dx. And this is from 0 to L. Then I can use u sub. Let u equals to x squared plus y squared. Then du equals to 2x times dx. I have an x in the numerator. If I multiply another 2, then I need to divide the 2 to cancel out. So this equals 20 divided by 2 times Coulomb's constant times y integral du over u to the power of 3 over 2. And this is for x equals to 0 to x equals to L. It equals 10 times Coulomb's constant times y. Then I have integral of u to the power of negative 3 over 2. Its integral would be u to the power of negative half over negative half. Then I can substitute the u back. So I have x squared plus y squared to the power of negative half divided by negative half. And the bounds are 0 to L. So this equals 10 divided by negative half is negative 20 times Coulomb's constant times y. Then I substitute the bounds. I get 1 over L squared plus y squared minus 1 over y squared. So, the net electric field at point P is 20 times Coulomb's constant times the vertical distance to P times 1 over y squared minus 1 over L squared plus y squared. And this is in the y direction only, so times j hat. Unit is newtons divided by Coulomb.